empezar la sesión de la tarde. Tengo el honor de presentar a Adolfo Guillot. Para que los que no lo conozcan, digo, muchos los conocen, pero los que no, Adolfo estudió la licenciatura en matemáticas aquí en la Facultad de Ciencias, luego hizo un doctorado en Lyon. Después de doctorado se integró al instituto en la unidad Cuernavaca en 2002 y posteriormente hizo un postdoc en Brasil y regresó y está en la unidad Cuernavaca y ahora lo tenemos felizmente lo tenemos en el Distrito Federal. No es nada personal con la gente de Cuernavaca. Y bueno, en términos de investigación, Adolfo se ha dedicado a estudiar las ecuaciones diferenciales, las acciones de Lie y bueno, en general, ¿no? Más o menos es eso. Y bueno, hoy nos va a hablar sobre Single Value Solutions of Complex Differential Equations. Pregunta, ¿he de repetirlo en inglés? No, ¿verdad? Bueno, es que vi el público y creí que es.
Okay. So good afternoon, everybody. I am very honored to be talking here. I wish to deeply thank the organizing committee for inviting me. And I would like to tell you some things about differential equations in the complex domain. So I will begin by talking about differential equations, and I would like to start from the beginning. This is the beginning. So Newton was investigating lots of things about physics, optics, and then he found something that he thought was very, very important, and he wrote about it. He was telling us about something, and then he says about his research, the foundations of these operations is evident enough, in fact, but because I cannot proceed with explanation of it now, I have preferred to conceal it. Thus, and then he gave us a secret. He gave us instructions, but he concealed these instructions. And then, sometimes later, we found what he wanted to say by this. It's an anagram. And here it is, what Newton wanted to say. In English, it means, given an equation involving any number of variable quantities, fluent quantities, to find the fluxions, the derivatives, and vice versa. He's talking to us about the fundamental theorem of calculus, in some sense, to integrate and differentiate functions. So Arnold, about this quote, tells he says that Newton wanted to tell us that solving differential equations is important. And the physics has proved this interpretation right, of course. We have all the 17th, 18th century to witness, and we were very happy. We had physics, and we could write differential equations describing this phenomena in physics. Some of them we could integrate directly. Some of them we took more time to integrate. But there were some functions that were deeply related to some differential equations that were deeply related to some physical problems that we had trouble understanding fully. One of them is the equations, or Euler's equation of the spinning top. So we have some solid moving in space. There's no gravity. There's just the masses of the inner masses of the body. And when you look at the evolution of the angular momentum of the body with respect to some particular fixed coordinates linked to the solid body, you find this differential equation. So it's omega 1, omega 2, omega 3 are the components of this angular momentum. We have some constants, I1, I2, I3, that depend on the size, on the shape of the body. And then we have some conserved quantities, two quadratic forms. So the motion of this angular momentum takes place along the intersection of a sphere in dimension 3 with an ellipsoid. So it's, in general, will be given by some periodic orbit. And these sort of equations we did not really know how to integrate. Because when you want to understand what happens, say, with the first variable, when you substitute the square of it and you replace all these unknown, and you replace by this conserved quantities, you find that omega 1 satisfies this sort of differential equation. The square of the derivative of omega 1 is a quartic polynomial in the variable. So these are what are called elliptic integrals, and we can solve them. We cannot really appreciate them in the real setting. We have to go to the complex one. So let me explain you how this is done. This is classical and historical. So you have some quantity, dy over dt, is some square root of some polynomial in y. So you can write it, say dt. You can separate the variables. So this is dy over the square root of this polynomial p of y. And so you need to integrate, in some sense, to obtain y of t, you need to integrate this. And this, the true nature of this integral is only evident when you look into the complex numbers. So let me tell you briefly how you integrate this equation. So you have 4 in the complex numbers. So let me picture here, this is the Riemann sphere. This is extended complex numbers. And you have 4 roots of that polynomial where your differential equation for the right-hand side is 0. So in the other places, you have 2 determinations for the derivative of omega 1. And this determination changes when you go around one of these 4 points where the right-hand side vanishes. So if you take here, you change. But if you go, so here, you change as well. But if you encompass also the other singularity here, you will not change. So what you can do is, you can draw some, you can cut along these 2 lines and find one determination of the right-hand side for the equation, and then you can also take another copy where you will cut also along the same 2 lines, and then this integral really will take place in this integral will take place in a surface, in a real surface that you construct by, when you go around this point, you should exit from this one. Then you go, when you exit in that way, you should enter here. So what you should do is you should put some cylinders here to identify. So what you get is the surface of a torus. And once you do that, you see that these singularities that appear here actually disappear. So what you have is, on the right-hand side, so you find after gluing that actually your differential equation doesn't really take place in a surface. It's in a Riemann surface. That's a torus. And here the differential equation is just, well, take the complex plane. How you parameterize, so it will be time. And how do you parameterize your torus? Well, you just, you can see what the vector field here, you can see what the motion is here by just identifying points differing by some two linearly independent translations. So once you quotient by this, you get the torus, and here the movement in complex time takes place. So actually you should, this drawing, when you see this curve, you should see it in complex 3-dimensional space, and then this curve will become a torus minus some points, and motion takes place there. So some features of real functions, of real differential equations, are evident when you look at them in the complex setting. So in the complex setting also, there are functions that are not really functions. There are functions that are not set theoretic functions, but that we still like to call functions, like the square root or the logarithm. But strangely enough, these sort of functions that we find in physics, they are not like that. We find functions that are true set theoretic functions, probably not defined in the whole plane, probably with poles or with essential singularities, but we find we find in these equations, the solutions are given by true functions. And then people started investigating what happened with these functions, and then a quest began to understand all the differential equations that have only single-valued solutions. So let me share with you this article by Guillot and Bouquet. And then they write some of the equations that look like, so it's probably too small here to be seen. So they want to see some, they try to understand the equations, not of the kind we just saw, but probably with higher degree root appearing in the right-hand side. And then they want to classify the differential equations that have only single-valued solutions. They call them monodrome solutions, by saying that when you continue one solution, you still have a solution. So they give a classification, but they do not really say this is the classification. They say here's the list of the equations we were not aware of. So we don't know what were the equations that they were really aware of, but they have some 12 equations. And there's some exponents here. Probably you see them, probably you don't. So let me briefly explain the geometry behind these equations of Guillot and Bouquet. So before that, so when we study this equation appearing in Euler's top, we find a sphere and we find a double cover that's a torus. Okay? So for the other equations that will appear, let me draw this lattice in C. So there's a lattice there. And if I take an hexagon and I identify the opposite sides by translations, there's some black ones, there's some white ones, I get also a torus. This torus has an order 3 automorphism given by rotation around one of the vertices. So this induces an order 3 rotation of your torus, and in the quotient, and this order 3 rotation will have 3 fixed points, and the quotient will be again a sphere. This time we will have 3 points over which we ramify, 3 ramification points above, 3 leaves, 3 branches that ramify above these 3 points, and that will give us, here's a cubic root, and here's some squares here. So these 3 points correspond exactly to this drawing I'm showing here. So this equation will also represent a torus that will cover, and when we lift the differential equation to the torus will be just the only differential equation in the torus, which comes from identifying torus with the quotient of the lattice. So we have for the other equation, we have the other lattices. So here you find a torus by identifying the opposite sides of the square by translations. You have an order 4 rotation, and so on. And we have yet another one. Here we have essentially the same torus as before, but here we are considering an order 6 automorphism. And this gives the complete, if you see this sort of, continued with this sort of geometry reasoning, you will find the list presented by Guillot and Bouquet. And the thing is, well, we really need to have, so what we have is we have the sphere, and we have some points, and then we take a ramified cover, and then we find some surface where we have a vector field. We find torus in general, or we might find some spheres as well, but we do not find higher genus surfaces. And the reason that why we do not find higher genus surfaces is because vector fields, holomorphic vector fields on these surfaces necessarily have poles. And when you have poles, you have multivaluation. Say, if you take the square root of t, the derivative is essentially 1 over square root of t. So this square root has 2 determinations, is multivalued, and solves the differential equation f prime equals 1 over f. Okay? So if you want to understand differential equations that do not have multivaluedness, then in one dimension, you should not have poles. So this happened around 1850, and then came Paul Painlevé, and he gave us a task. So he said, integrate all differential equations. And he said, well, no, not all differential equations. He said, consider all algebraic differential equations. And then he said, understand those that do not have multivaluedness. And he writes that explicitly, integrate all differential equations. However, he gives us a hint on how to proceed. He says, start from those of smaller order. And he did start, he did accomplish part of his goal, and he showed us some special functions, some second order functions that have a clue, have the key to understanding multivaluedness in differential equations. And these are the functions that we call the Painlevé transcendents. So these are functions that cannot be solved by, in general, by elementary functions. You will not find trigonometric or other sorts of, or even elliptic functions that will solve these equations. And they are related, they may present some multivaluedness, but they are related to this problem of absence of multivaluedness. And what Painlevé did was, one of the techniques of Painlevé was the alpha method. So he says, this property, so he was studying this property called that we now call the Painlevé property, which we call the absence of movable critical points. And so he says this property is stable under, it's a closed, in some sense, it's a closed property. It's a property that is closed in the space of differential equations. So if one equation degenerates into another, and the limit one has this property, well, let's say, and if the limit one does not have this property, then it's because the original one didn't have this property either. So let me illustrate this method in one setting. So you see all of Painlevé's equations are second order equations, and on the right hand side we have the derivative of y up to with some, it's a quadratic polynomial in the differential of y, just like the first equation. And if you introduce a parameter, so here you do not really change anything. I just made a scaling in time. But if I make the equation degenerate by making alpha go to 0, I find this differential equation, which is much simpler, assuming that t is not a pole, assuming that t is just one of the special cases. So we find another equation, which is homogeneous, because, of course, if I make now this substitution, I will not change the equation, which is simpler, and which, before knowing how to integrate the more complicated equation, I should know how to integrate this simpler equation. So if you look at this equation, and if you see, if you take a look at the equations studied by Guillot and Bouquet, we had this sort of equation. And you will see that, in fact, when you derivate this equation, we'll find some constant u squared. So actually, it is not difficult to see that this L should have poles. So this equation, the simplified equation, actually belongs to the list given by Guillot and Bouquet. So this is the general strategy for, this is one part of the general strategy for Painlevé. Can you please stop the cell phones and the... Thank you. Okay, so this is Painlevé doing his work on second order equations. And of course, second order equations is the beginning of a tower. Well, first order equations were understood. And then there was an effort to understand third order equations. This was made by Chassis. He was an astronomer, and he also had these studies in differential equations. And Chassis sought to understand the equations of the third order that did not have this multivaluedness. And he knew that we should start with homogeneous equations, so you get a third order equation that's very general, so you should use this alpha method of Painlevé to make it degenerate into some sort of homogeneous equation, and then you start establishing which one of the homogeneous equations you should understand. You should understand these homogeneous equations, and then the idea is to proceed. But in fact, he did not quite finish this. He found this equation. This is it's a third order equation. It's a very naive looking equation. You can write it as a vector field. So you have some sort of vector field in C3. And Chassis proved that we have a differential first integral. So he says we have some variety in C3 given by a degree 10 polynomial. In fact, this equation is quasi-homogeneous. If you give x, y, and z the weights 1, 2, and 3, then you see that this vector field is homogeneous, and that this first integral is also homogeneous as well. And for this equation, Chassis did not know how to solve it, and he says, well, I think you might be able to solve it by elliptic functions. If you see this equation, if you make the substitution a phi at, you will get, again, a solution of this equation. It is homogeneous in that sense. And this is around 1911. And in fact, Chassis's work sort of stopped there. A lot of work around Painlevé equations took work in Russia and Japan. But Chassis's work was sort of overlooked, and we had to wait around 90 years to get the solution of this equation. So let me tell you what the solution of this equation looks like. So we had a first integral, so we can restrict our vector field to say a generic level set of this first integral. So we have something very explicit. We have an affine variety in C3. We have a polynomial vector field in it. And the question is, well, can we integrate it? Can we say something about it? So let me tell you Cosgrove's answer, Christopher Cosgrove's answer to that question around the year 2000. So the idea is the following. Consider in C2 a lattice generated by these four vectors. So we're in C2. And we have a lattice. So I know how to draw a lattice in C2. So this lattice has an order 5 symmetry. You can act linearly in C2, and you will find by this order 5 matrix, so zeta is the fifth root unity, and you will preserve this lattice. So you will get a complex two-dimensional torus that has some order 5 automorphism. And so if you want to think in terms of Jacobian, we saw Jacobians this morning. It is the Jacobian of this curve of genus 5, which has an order 5 automorphism given by just multiplying x by this fifth root of unity. And this action in C2 is linear, so it preserves, so both coordinate vectors are invariant under multiplication by this matrix. They are eigenvectors. So you may consider the vector fields that they generate. And then you can find there are two special vector fields. Let me label Z, the one that is associated to zeta square. And then what the solution of Cosgrove is, for the Chassis 9 equation, it says, well, this is the Chassis equation in restriction to one level surface. And what he says is you can take this affine variety with its vector field, and you can embed it into this complex two-dimensional torus. And that's the solution of the equation. So he did this, he did much more. He achieved Chassis's program for three-dimensional third-order equations. And let me go back to Chassis's question. So Chassis, well, he had a hint. So in general, we can ask. So we have an affine variety. We have a vector field. And if you suppose that the vector field has no multivalued solutions, you suppose this, then what can we say a priori about it? So of course it might be solved by elliptic functions. It might be solved by hyperelliptic functions, but can we say something more? Can we give some, is there enough information to give some, can we say something more about it? Can we at least partially solve, in general, this question by Chassis? So, in order to do so, we have this problem in general, how to, given a polynomial vector field in an affine variety, so what can we say about, how can we understand this multivaluedness of solutions? So one idea is to compactify the affine variety into some projective variety that's now become compact. And when we compactify, our vector field, which was polynomial, will become some rational vector field, some meromorphic vector field. So this is a good setting to work. Actually, we can work in a more general setting. Probably we can work in the setting of meromorphic vector fields on compact complex surfaces, and that's where this theorem takes place. It's a theorem in collaboration with Julio Rebelo from Toulouse, and it says the following: suppose you have some meromorphic vector field on a compact complex surface, like the surface you obtain when you compactify an affine variety with a polynomial vector field, and then desingularize it. And then what we do is we give some birational theorem, with some result that will not tell you what your manifold is, but what your manifold is up to some blowing up and blowing down of some points, as we heard yesterday from Professor Mori's talk. So up to blowing up or down some points, you have the following. So either your vector field is holomorphic. This is the situation here. So we added some things to infinity, and then we found some variety where my vector field was holomorphic. The other possibility is the vector field to have a first integral. The orbits are not really moving all around your surface, but are constrained to live within algebraic curves. So this is setting another possibility. And the third possibility is that your vector field preserves a fibration. This is, we have a family of curves in our surface, and then what our vector field does, it moves one of these curves into the other. And it acts not really, it acts on this surface, but in fact, it actually acts on the curve given when each curve here is identified to a point. So you can think of this as a separation of variables. And the way to prove this theorem is to understand first what's the problem here is we have a polynomial vector field, and when we compactify, we have something that's given by poles. We add the vector field, which was polynomial, gains some poles at infinity. We said that we didn't want poles, but in fact we don't want poles along the solutions. But we are okay if poles arrive in a way which solutions cannot see at all. So if the solutions and the poles look like this, there's in principle no this phenomenon does not happen if the solutions went across the curve of poles. We would have some problem. But here, it is not evident what the problem is. Okay, so we started trying to understand how to simplify or how to modify this locus of poles, because if you modify the locus of poles and you make it disappear, you end with a vector field that has no poles, that is holomorphic, you're done. So there should be some structure. So if you cannot get rid of the curve of poles, well, can you at least give a simple description of it? So what we did is, first we established that we gave in some sense a normal form, a description to which you can take any curve of poles of the vector field. So the curve of poles after these blow-ups or blow-downs might be a rational curve, a sphere. It might be also an elliptic curve, a torus. Or it might have a lot of rational components, a lot of two-dimensional spheres arranged. So I'm given here, so it will be an arrangement of this sphere, of these rational curves in the surface. These are what are called, at least that part, are what is called the extended thinking diagrams. We saw some thinking diagrams in the Christoph's talk. So those were the classic thinking diagrams. These are the extended ones. So we are in a surface, in a complex surface. This is a four-dimensional real manifold. And we have spheres. We have many of them. And we can construct a graph in the following way. So give me a vertex for each one of these spheres and put an edge between two of them if they intersect. So there's more information to this diagram I am not showing. But we can prove that these are in some sense the limit configurations of curves. These are the curve of poles up to some blowing ups and blowing downs. And if you're acquainted with the geometry of surfaces or the classification of surfaces that Professor Mori was talking about yesterday, you had probably seen some related diagram in Quieres' description of elliptic fibrations. So I will not say a lot about it. Let me just say that. Well, I will say something about it. So suppose you have elliptic curves, and you have a lot of them. You have a complex curve of elliptic curves. We saw that there are some elliptic curves that have automorphisms. I have, for example, order 3 automorphisms. So you might construct some automorphisms of this situation by doing the following. So here I have a disk. It's a one-dimensional complex curve. And I may construct a global, in some situations, a global order 3 automorphisms, say by rotating here by some order 3 transformation, and then applying my order 3 transformation to all the elliptic curves here. So I will act in general nicely away from this elliptic curve. But here, I will find in my, for the quotient of this elliptic curve, with its 3 fixed points, I will find, as we saw, one sphere. But then, at these 3 points, I will find some singularities, some mild singularities, but singularities as well, that we can solve. And once we solve these singularities, we find, for example, this configuration. So when you see this configuration of curves, of rational curves in the surface, you should think that it comes from one of these situations. I have a fibration, what is called a fibration of elliptic curves, and that I had a quotient by some finite order here. Okay, so you should think of them as elliptic curves, as degenerate elliptic curves. And I'm saying that this is You see, this is much like the situation of Painlevé and Briand-Bouquet. So they said, when these equations degenerate, at the end I see something whose description is related to these elliptic curves with symmetries. So here as well, I do not really have this degeneration. I have an ambient two-dimensional complex manifold. And then I have that, in some sense, if you think of this curve of poles as something that happens at infinity, then when I approach infinity, I find one of these symmetric elliptic curves giving the description of what happens at infinity. And in fact, if you're in a... So this is just combinatorial, but we do not know exactly what the situation is like when we look at this configuration of curves in general. But if we're in a compact manifold, then we know that there's a fibration that comes with this drawing. So from all of these curves, which are in some sense hints of vibration, we get this vibration, and either your vector field will be tangent to these fibers, then we have a first integral, or transverse, and then we will preserve this vibration, or if we are able to make this this curve of poles disappear, we find the holomorphic vector field. Okay, so this is one possibility that we may give more detail to it. So if you have, if you're like in the setting that we started with of an algebraic and affine surface with a algebraic surface with a polynomial vector field, you will find some variety which is algebraic, then Keller, and in fact we understand very well. I don't know, probably Kodaira, probably earlier. We understand very well what holomorphic vector fields are on algebraic Keller surfaces. So most of them, so all of them either preserve a vibration or they are related to complex tori. Okay, so you can, if you do not consider in general compact complex surfaces, but say algebraic ones, you may replace this X is holomorphic by, you have a complex torus and you have a holomorphic map, a holomorphic vector field in this complex torus. So the situation is different for the non-Keller setting. So it was just, the full classification was only obtained 15 years ago by Bluski, Olger, Klaus, and Thoma, who finished the classification of vector fields, holomorphic vector fields on surfaces. And the difficulty is that we know very little about non-Keller. We know a lot, but not enough about non-Keller surfaces. That they do not fit nicely into the Enriquez-Kodaira. They do fit, but we do not have a complete classification in the non-Keller setting, contrary to the algebraic setting. I will come back to this classification later. Okay, so this relates a lot to, so there's a lot of people who have been interested in understanding polynomial vector fields in affine varieties. We have this extra property that not only they are single valued, so they have single valued solutions, but they actually have solutions defined for all time, so that they induce some biholomorphic mappings of this underlying algebraic varieties, not necessarily algebraic mappings, just biholomorphic. So let me just give two statements. There's one by Marco Brunella in 2002. We can consider complete polynomial vector fields on affine surfaces, and Brunella gave a classification that has common elements with the theorem I just stated. He proved that, building on work by McQuillan and Suzuki, he proved that they preserve rational vibration and then classify them up to polynomial automorphism. And more recently, Kaliman, Kutschenbauch and Leuenberger gave for general algebraic surfaces a complete description of how curves are arranged at infinity using this fibration, the existence of this fibration. Okay, so the tools that I just described, that I'm not really saying how do we prove this theorem, how do we conclude that this the structure or the configuration of curves is this one. Let me tell you other things that we can deduce by the same tools. I know I am skipping some parts here. So in general, what we have is some way to understand combinatorially curves, invariant algebraic curves or invariant curves in surfaces. So another situation is the situation, so I will change a bit of setting. It's the same as it's vector fields and surfaces. So let me change a bit. So suppose you have a complete vector field. So you have a complete vector field, X. So you have an action, holomorphic action of the group of complex numbers on a space. And suppose that you have one singular point of your space. So you may ask, well, how compatible are these two hypotheses? How singular can a singular point be in the presence of a complete vector field? So this result gives an answer. In the case, my space is what is called a Stein space. So Stein spaces include affine varieties, or the analytic version of affine varieties. And so if you have a Stein surface, two-dimensional, and you have some singular point, and you suppose that the zeros of X do not accumulate to your singular point, then you can be very explicit on what your singular point is, and in some situations much more. And this is the content of this result. So you have this Stein space, and then what the result says is that you only have two possibilities. So the first one is what is called a quasi-homogeneous singularity. So you have some, for example, a homogeneous singularity is quasi-homogeneous. So you have one homogeneous polynomial, and then you just act by multiplying by some non-zero complex number. And you can do so also for the quasi-homogeneous setting. When you give different weights to different variables, you will need to weight your alpha as well. So this is the first possibility. And in fact, when you're in this first possibility, you actually know there's a result by Camacho, Movasati, and Descadua that says that if you're in a Stein space and you have an action of the multiplicative group of complex numbers minus zero, actually your Stein space is an affine variety and your action is algebraic. You're just looking at it in the wrong coordinates. So in the first situation, you get, just by supposing that you have one singularity, in some sense, these two hypotheses imply too much. No, it's too much to ask. So you have the situation. And the second situation is that you have a cyclic quotient singularity. If you're in C2 and you have some nth root of unity and you act linearly on C2, then the quotient under the action of the group generated by this map has some singularity that's called a cyclic quotient singularity, and that's the only other option you may have for what the singular point of the vector field and of the whole space may be. So, and this is essentially with the same tools as the previous theorem with Giulio Rebello. When you have one singularity, you can disingularize it. So you replace, in fact, this point by some curves in such a way that when you considering that singular point is the same thing as collapsing all this set of curves into a point. And here is essentially the same setting. We had an analog setting of the one we had before. So we have a vector field, and we have a curve which is invariant under the vector field. So you can do an analog. You can try to make the combinatorics again, and in this Stein setting, it works very well. So this is another result, and let me just. I told you before that there's this theorem by Gluski, Wojciech, Laus, and Thoma, where they classified holomorphic vector fields on compact. They finished this classification. The classification has been going on for a long time. So there's some things that we know from a very long time, but there's this dark side of complex surfaces called the 7-0 class, and they finished this classification by classifying the surfaces in this class. This class includes Hopf surfaces, Kato surfaces, and they finished the classification of vector fields in this class. And that's interesting because we do not have a classification for this class. We do not know if the conjecture is that every surface we know in this class is one of the ones we know of. But it's just a conjecture. The conjecture is that all the missing equations all the missing surfaces are what are called Kato surfaces. So they did this, Gluski, Wojciech, Laus, and Thoma did this classification for the 7-0 class. And in fact, using essentially the same tools as I have described, we can give a simple proof of the results. I will give a statement, but the idea is the same. If you have a compact complex surface and you have a holomorphic vector field, you will find some invariant algebraic curves. These invariant algebraic curves, if there's a lot of them, you know, all the things we know of surfaces tell us that there cannot be many invariant curves unless we have a fibration. And if you work, we have the same setting. We have complex surfaces. We have a holomorphic vector field, which is in particular complete. So its solutions are always single valued. So we can use the same sort of combinatorics, and we have this. You can give this statement in a very not expensive way, let me say it like that. So with the same combinatorics. So this fits into the classification of holomorphic vector fields on surfaces. I'm not giving you the complete statement. Just let me give you this statement that can be really easily obtained by the same sort of argument. So you have a holomorphic vector field, which is not identically zero, on a complex surface, and you assume that it has some zeros. If it doesn't, like in this case, then you leave it out. And you suppose as well that it does not induce an action of C star. It does not all the solutions are periodic with the same period. So under this hypothesis, you can conclude that either your surface is rational or ruled. In this case, you understand the surface. You understand the surface. On the second, your vector field has a first integral, so you can see your surface as a disjoint union of curves, and your vector field will be tangent to them as algebraic curves. your vector field will be tangent to them. The fourth possibility is that S is one of these surfaces that fall within the 7-0 class, Kato surface. And this is very strange because they really fit in a very interesting way in this classification, Kato surfaces. And the fourth possibility is that your curve, your algebraic invariant curves, is actually one of the curves that we saw in this extended thinking diagrams. So in particular, you will have some divisor in your surface of self-intersection 0, and then you can continue with the classification from this data. For example, here you will find these Hopf, Enoki surfaces, elliptic vibrations coming from this third item of the classification. So I will stop here. I thank you very much for your attention. Yes.
You said something like you perform some.
So in general, when I have in a complex surface, when I have in a compact surface, say, when I have compact curves, I can draw this diagram. So with 1 point for each curve, you can actually give weights. So I can count the intersection multiplicity and draw as many edges or as the multiplicity, and I can put it also into this diagram, the self-intersection of a curve with itself. So there's more to it than just the graph, and that I can build always. So what I'm saying is that, so in general, for this problem of deciding whether the solutions of your differential equations are multivalued or not, you really don't mind if you blow up or down some points. So this property will be invariant under blow ups and blow downs. So under birational transformation, binomorphic transformations. So what I'm saying is, in some sense, it's a baby minimal setting. So you can. So I don't know. It might be very complicated because if I have some curve of poles, I may blow up a lot of points and give some very complicated diagram, but it is unnecessarily complicated. So I may start blowing down some points and rearranging the combinatorics. And I said, I can always guarantee you that if you have no multivalued solutions for your vector field, at the end you find one of those, the combinatorics is one of those described by the extended thinking diagrams, which are also called Kodairo's list of singular elliptic fibers. Yes, as yesterday in Professor Morris' talk, if you find a -1 curve, you blow it down. So you have a curve rational curve with self-intersection -1, you blow it down, and then that's so probably you have to blow up a bit at the beginning, but after a certain time, you just start blowing down all -1 curves. Alberto? With two, yeah. I think there are some, but I think, so I heard from Marco Brunella the following question. Is there a complete holomorphic, not more polynomial, but holomorphic vector field on C2 with an infinite number of singular points, of equilibrium points? I don't know. Probably all of them. Okay, so I don't know. So this is. combinatorics is because you have multivaluedness somewhere. So you can actually use this combinatorics to exhibit multivaluedness. Well, the first obstruction will be, so if you have one trajectory that goes across the curve of poles, then certainly you will have multivaluedness along the solution, and in fact, along many solutions neighboring this one. But you can use this as some sort of, you can try, if you do not have this sort of things, you can use this as an algorithm. We have listed a lot of obstructions and then seeing that these obstructions lead to this combinatoric.